Okay, so I think it's time to start our morning session. I hope you enjoyed your free afternoon yesterday, and I hope you went around in Stockholm to visit some nice places. So today again, we will have the same format, two speakers plus question time, and then panel discussion in the afternoon. And we will start with Daniele Oriti, who will tell us about tensorial group field theories for quantum gravity. Please. Where the dinner? Oh, the dinner. We send an email, yes.
Okay. Can you hear me okay? Good. Fine. So let me start by first thanking the organizers for the invitation and the opportunity to speak. And then let me continue by blaming the organizers. They've been extremely nasty. They forced me with the threat of violence to give an introductory talk to the formalism of tensorial group field theories, and they've been very explicit of just introducing the formalism, links with other approaches, and not presenting new results, which was my original idea. With a lot of bravery, I actually included towards the end at least a brief survey about results. And then it will be up to you to ask more about the new results to circumvent the limitations imposed by the organizers. Anyway, let me start. So I will first just really introduce the general ideas about the formalism and emphasize how it connects to other quantum gravity ideas. So tensorial group field theories is many different type of models, and the single feature that suggests to put them in a unique, in a single category, is the fact that there are field theories with the dynamical variable being a tensorial field, but with a specific type of combinatorial non-locality in the interactions. And a good part of the initial part of the talk would be to explain what I mean by this combinatorial non-locality. The generic result of this combinatorial non-locality is that when you draw diagrams corresponding to the interaction processes, they are going to be dual, not to graphs, the usual Feynman graphs of local quantum field theory, but to cellular complexes with all the added complications and, well, mathematical interest if you're a mathematician. So that's the first point. The exact type of tensor you have could be, a tensor over some finite index set, or a tensor over a group manifold, that model dependent. In fact, you have a lot of different models with different ingredients, and the differences have to do with the domain of the tensor indices, the fact that you may have additional local variables on top of these variables which are then combined in a non-local manner in the interactions, the precise combinatorial structure of the interactions, and then, of course, the specific choice of model, choice of propagators, of interactions, presence of additional symmetries, and so on. All of that is model dependent. There are, in fact, two main classes of models, each quite rich. The first one, and an example of a model in that class is here. So you have a tensor field. You have here indices that take value from S1, rank 3. So on the momenta, or you can just take some discrete set, and if you put a cutoff on the index set, then it's a finite one. There is some non-trivial way of combining indices in the kinetic term, and then the interaction terms are tensor invariants of these indices, ways of contracting tensors. This type of models with dynamical non-local arguments and a simplicial interpretation for the field will give, in general, amplitudes which are in relation to lattice gravity path integrals, ways of writing down gravity, gravitational theory, but on a lattice. And in fact, in this class, you're dealing with theories of random discrete quantum geometry. And it is this type of models which have a number of links to lattice quantum gravity, loop quantum gravity, and spin foams. A second class of models deals with just tensor fields on flat space. So there are additional local variables which are embedding coordinates in flat space. And so you have only these local variables which are treated as dynamical ones, and all the combinatorial structure is somehow internal, some auxiliary internal structure. Of course, you know already an example of this. If you think about it, I mean, Yang-Mills is a local theory for a matrix, which is the potential, the Yang-Mills potential. It's valued in some representation of the gauge group. And so these are tensor field theories in flat space, and the connection to quantum gravity of this type of models is much more indirect. They are mostly explored in order to define new, interesting conformal field theories, and the application to quantum gravity is through the ADS-CFT correspondence. I will mostly, well, in fact, only deal with this type of models here. So if you want to understand what I mean by combinatorial non-locality, you have to, first of all, keep in mind what we mean by combinatorial locality in local quantum field theory. Take a theory of a complex scalar field. The domain of the field is the spacetime manifold. The quanta are point particles. And if you want to graphically represent a point particle, well, that's impossible, but you just have some dot with the variables, the data, the degrees of freedom associated to the point particle encoded in some index. When you go to do the usual Feynmanology, the fact that the interactions are local, so that point particles interact at a point, or that field arguments are identified at a point, means that the combinatorial structure will give you some link associated with the propagation, some line. It's a graphical representation of what is going on, and the local interaction is the fact that you have some node of interaction where the fields arguments are identified in position space. So this is the interaction kernel, propagator. You can change variables and you can go to different representations of the Hilbert space, as you know, go to momentum space or whatever other basis you like. And the fact that you have this locality of interactions means that when you look at the action, the field arguments are identified here at a point with this type of kernel. So the graphical story is that because of this, you have graphs. You generalize that, and we know already, I mean, most of you, I think, know an example of this is matrix models. In matrix models, dynamical variables are given by matrices. There are two indices over some finite set. If you want to have a graphical representation of the quanta or the objects that are actually dynamical, well, then you have to think of them as associated with links with the two indices, the two endpoints. That represents a matrix or the quanta of the corresponding field. Propagators will have to keep track of both indices. So a good representation to do that is to use a stranded diagram dual to the matrix that is propagating. And the interactions are usually constructed so that the indices of the matrix are identified, of three matrices coming to the interaction, are identified pairwise. And the identification is the gluing of the three edges corresponding to the three matrices in the interaction at the endpoints. And so it gives you a triangle. That's one example, of course, is the example in which you have an order 3 interaction with the trace invariant, which is just a cyclic product of matrices. For this is a specific model. It's very simple because you can choose, for example, kernel for the propagation and the interaction given just by Kronecker deltas. You don't complicate stuff, you just glue things together. The result of this, however, this is the combinatorial non-locality I was mentioning, because the indices, the arguments of your field, are not all identified. They're identified according to some combinatorial pattern. Okay, pairwise here, according to this pattern here. This gives to the interaction a simplicial interpretation because, as I said, it has the combinatorics of a triangle, of three edges glued to form a triangle. When you look at the diagram, you have to keep track of all these combinatorial pairings. The result of this construction is that for this specific model, a typical Feynman diagram is going to be combinatorially dual to a triangulated two-surface, because you're just gluing triangles in all possible ways. So when you write down the dynamics of the theory in perturbative expansion, so in Feynman diagrams, this combinatorial structure of the processes it's such that you have a sum over all two-dimensional simplicial lattices on any topology, because you didn't put any restriction in the model. And so you're just gluing triangles in all possible ways. You have to do it, otherwise you're not doing quantum mechanics. Everything that is possible has to be there, unless you decide to make it impossible by changing the model. So you get a sum over lattices of all topologies in 2 dimensions, and obviously the model is purely combinatorial. I didn't choose any fancy kernels in the action, and so you just have combinatorics. You can relate it to discrete gravity by assigning basically the graph distance, considering the triangulations as equilateral, so without introducing any additional variable. And you can put in correspondence this combinatorial amplitude with a discretization of gravity on a two-dimensional equilateral triangulation. So what you get is a sum over all geometries for given triangulation, where all the possible geometries are just all the possible equilateral triangulations for given topology, in the same spirit as dynamical triangulations, but you also summing over all topologies. In this sense, you have a lattice gravity path integral interpretation for what the model gives you. Sorry? Here, yes, because a priori I can do quantum mechanics, but indeed this one is in fact related to the Euclideanized version of the theory. So it's e to the, if you want to interpret the amplitude, these are e to the minus the discrete rejection. Later on, for other models, you see that these models, even in the Riemannian context, so Euclidean signature, do correspond to e to the I action for Riemannian geometries. And it has to be like that, and I can explain why. Anyway, so you have a sum over topologies. In matrix models, it is well known that in large and limit, only planar spherical topologies dominate, because the amplitude is basically already a topological expansion governed by the Euler characteristics. Yes. I call it an amplitude for the same reason why you need the I there. And you can do it for non-trivial boundaries, so you really are talking about some transition. You can talk about the transition from initial to final, or ampli associated to some boundary state. Okay, there's an immense list of results for random matrix models, and they all go beside my point here. Combinatorial non-locality generalized. The same idea, but instead of working with the matrix, you work with a tensor. This is an example of a model. So rank 3, finite index set, and the graphical interpretation or representation is that you're dealing with the triangle with the indices labeling the edges of the triangle. Then you choose a particular action. Again, the simplest one you can think of in this simplicial context is that you glue the indices, you trace the indices of 4 tensors in the interaction with a certain combinatorial pattern. And this combinatorial pattern is the one of 4 triangles that glue together to form a tetrahedron, a 3-simplex. The idea is that this model will give you a sum over 3-dimensional simplicial lattices, all possible ways of gluing tetrahedra together. These are typical Feynman diagrams. The boxes and circles is because you can have additional symmetries on the tensors, but look just at the combinatorial structure. Clearly, you have much more structure than in a Feynman diagram. It's not a graph, it's really a stranded diagram, and it has to be with this additional combinatorial structure because you're encoding 3-dimensional simplicial complexes. You can play the same game. So you get all 3-dimensional topological manifolds. In fact, it's worse. You get also singular topologies, but the only thing you're doing is gluing together tetrahedra in all possible ways. There's no manifold condition that is imposed in this model. Again, for this particular model, the amplitudes are purely combinatorial. It's super simple. I only paired indices by tracing and nothing else. So a purely combinatorial amplitude, which depends on the parameters on the model and the combinatorics of the diagram. Hey, I'm just introducing the models here. Then I'll tell you a bunch of results and what we know, what we don't, and what is not covered. You can ask and tell you whether we know something about that or not. So you can generalize the same simple type of models to any rank, so to any dimension. And the story is the same. Because the amplitudes are purely combinatorial, the only metric or gravity interpretation you can give is in the same spirit of matrix models or dynamical triangulations. You interpret these triangulations as equilateral, and you can show that by appropriate identification of the parameters, your partition function looks like, can be interpreted as a sum over all 3-dimensional, d-dimensional simplicial complexes weighted by the exponential of the Regge action discretized, applied to equilateral triangulations. So the tensor model doesn't give anything else than this sum, than this dynamical triangulations definition of the quantum gravity theory. It gives just a generating function for that. But because this gravity interpretation arises in a perturbative limit, in principle, it gives you also an access, a way to try to go to a non-perturbative sector, in principle. Now, this was a particular simple class of models. I hope that the idea of combinatorial non-locality is clear, because I will keep that, and I will do something else. Another class of models is obtained by taking the same combinatorial structure, but adding data, as if summing over all possible, including singular topologies, was not complicated enough. You add the quantum geometry data. And again, I give you an example first. Same combinatorics of the rank 3 tensor model over a finite index set that I gave you earlier. simplicial interaction, but now the field domain is some, I apologize with the model, I call it auxiliary, and then I'll try to explain, to give the idea for why it's not auxiliary, it's actually physical data, or it's supposed to be physical data, but it's a field over 3 copies of a group manifold, here SU2. But the way in which you convolute the fields over such arguments in the interaction is exactly like you were tracing over indices over a finite set in the simple tensor model I shown earlier. The other difference is that you also impose a diagonal left invariance under the action of the group on the field, which is quite crucial, in fact. Now, it's a model that whose only real complication is, again, the combinatorial non-locality. On the domain of the field, you have some metric structure, the Killing form on SU2. SU2 is a sphere, so you also have a topology, and so on. And it's a quite simple model, apart from this non-locality of the interactions, because I don't even put here a kinetic term with some differential operator on the group. It's really a simple model. Well, you do the same story, and this part of the story is like in the other case. You sum over all possible imperturbative expansion, you end up summing over all possible gluings of tetrahedra, so gluings of 3 simplices. The amplitudes now are non-trivial, are not purely combinatorial. I've added this type of group theoretic data. This symmetry here brings additional structure to the amplitudes and is a crucial structure. And what happens is the following. If I have a function over SU2, I can write it as such, as a function on a group manifold, but I can also do a different Fourier transforms, group analogs of the Fourier transforms. By Peter-Weyl decomposition, I can expand that function in irreducible representations of the group spins. I can do fancier stuff depending on the representation I choose, so a basis on the Hilbert space that I choose to write my amplitudes. The amplitude for each Feynman diagram takes different forms. Let's look at this one. When I do the calculation, in practice, the only dynamical variables end up being these group elements that impose this invariance of the field. This, if you trust me or you know about it, is a lattice gauge theory formulation of 3-dimensional Riemannian quantum gravity, which is topological BF theory in a first-order formalism. If you put it on a lattice, you write down the amplitude, you end up exactly with this. There is a flatness condition on every dual face, which means a flatness condition on every edge of the triangulation. And this is exactly what 3D gravity will do without cosmological constant, without matter. You just a flat theory. And so you end up with an amplitude which is not only non-trivial, but exactly a lattice gauge theory formulation of BF theory in 3D or 3D gravity. With the SU2 group elements understood as a discretized connection for the SU2 internal symmetry group of first-order gravity in 3D in the Riemannian context. You could do the same thing with the Lorentz group, and you would have the 3-dimensional Lorentz group, but then the amplitude would be more badly divergent, and you have to take care of what you compute. You can do Peter-Weyl decomposition, as I said, expand everything in representations of the group, spins. And the amplitude takes this form. This is a well-known and very old, in fact, formulation of the same theory, 3-dimensional gravity, on a lattice, and is called the Ponzano-Regge spin-form model from 68, first written down. So it's again, you can understand it again as a lattice sum over geometries, but expressed in purely algebraic language as a sum over group representations, the spins, associated again to the edges. and the interpretation is edge lengths. The spins, the value of the spin gives you the length of the edge to which it is assigned. If you come from canonical loop quantum gravity, this is the sort of model you will get when you try to write down a path integral for your spin network states. You do a fancier type of Fourier transform, you go to a representation of the same Hilbert space in terms of a non-commutative function of the algebra of SU2. The algebra elements are understood and can be obtained as the discretized triad. And you end up with this other expression for the amplitudes, which is the direct discretization of a first-order formulation of 3D gravity, with this Lie algebra element integrated with the Lebesgue measure, understood as the discrete counterpart of the triad. And then here you have the holonomy around the dual face to the edge, which is the discretization of this curvature in the action. Of course, I'm skipping all the technical stuff, but the point here, the message here is that you have the same combinatorial structure that I said earlier that allows you to talk about simplicial lattices and summing over them in the expansion with all the complications that that entails. But then now, because of the additional group data, you have non-trivial Feynman amplitudes for each lattice produced by the model. And the interpretation in terms of lattice gravity now is in terms of less trivial discretization of gravity because you have dynamical metric data on each lattice. They're not equilateral lattices. The type of data change depending on the basis you choose, but in all cases, you can relate for this model to three-dimensional gravity, lattice gravity. Yeah. So H, all this, wait, I think I pressed the wrong button. No. It's the projector. Okay, I try to now approach the answer from a different angle, just in case. Okay, so I use really all the buttons in my pointer. Okay, so these are all SU2 elements. H are SU2 elements. They are associated to links of the dual complex, like you would do in lattice gauge theory. When you take concatenated products of those links along closed loops, you get this type of products. They correspond to this big H, which is the holonomy around a face dual to an edge of the triangulation. And that's where curvature is supposed to be located in a piecewise flat 3D context. And so that's why I say is the counterpart of this F, of the curvature of the connection. The H, small h, are the counterpart of the discrete of the connection itself. Big H is this holonomy, and so is the counterpart of this F. And the X here are the discrete version of the triad, Lie algebra element. If you smear a one form valued in Lie algebra along an edge, you get just a Lie algebra element associated to the edge. The J are basically the eigenvalues of the modulus of the H, of the X. So this is what you get when you work in a basis of eigenstates for the edge length. Okay. It's a coupling constant. Sorry, I forgot it. Here is lambda, not one. It's the coupling constant of the interactions. Not at this stage. You can, of course, restore dimensions and relate. You can put dimensions on the triad here, right? Like you would do in reg calculus. So you can put 1 over g here in the action, and you will get a 1 over g here. So you can restore all the dimensional quantities, but I'm working here with dimensionless variables. What? Mg. Well, it scales clearly with the number of simplices. If it would be directly the volume is the simplice were equilateral. Yes. Well, yes. I mean, I can talk about that. But the idea here is that you work with dimensionless thing and you try to reconstruct in a continuum effective description what is the physical interpretation of this parameter and any other parameter you may have in the model. If I get there, I will show you an example at the end. Okay, so in fact, you can show that that this will be related, well, not in the three-dimensional case, but in the other case, I will show you that I can say that it is related. You can relate it to the cosmological constant. My point here is just to say that you can give this type of interpretation at the discrete level here, but as you know very well, what happens in the continuum could be very different. And so I prefer to keep the parameters or the couplings here as they are, and then look for their role in an effective continuum dynamics. But yes, at the discrete level, you're definitely right. Okay, so you have here, sorry, so once more, you have a sum over simplicial topologies and over quantum geometries for each topology, with the difference with respect to the previous model is that already this sum over geometries for a given lattice is non-trivial. In fact, computing these amplitudes, depending on the diagram, can be highly non-trivial. Okay, I give you another example of model just to dispel any doubt that you can do only things in the Euclidean or only in 3D or 2D and so on. Well, I just flash the action for two models for four-dimensional Lorentzian quantum gravity. And they are the two models that correspond in a group field theory language to the most studied spin foam models for four-dimensional Lorentzian quantum gravity. And you can see, you should be able to notice that the algebraic analytic complication scales with the dimension. I mean, they become more complicated. This is the action for the so-called EPRL model. And this is the action for the so-called Barre-Cray model for Lorentzian 4D quantum gravity. Now, again, the detail of the action are not so relevant. The point is that I written them in, the first point is that I have the same simplicial combinatorics. So 4D lattices are going to be generated in the perturbative expansion. And that the quantum geometry of such simplicial structures is encoded in group data in this model coming both from SU2 and SL2C. And you have to be careful with the relation between these two subsets of data. That's where the quantum geometry is encoded. Or they can be encoded for this other model in pure SL2C Lorentz data. And the other point is that you're now, when you look at the details of this amplitude, you're encoding, you're endowing the simplicial lattice with the generalized, in fact, Lorentzian piecewise flat geometry with local light cones for each simplex. And we have already touched in some of the discussions the complications of having, putting together properly the light cones and having a nice global Lorentzian geometry. But again, the general story. The domain, okay, I wrote it in the representation basis. Otherwise, it would be the Lorentz group or the SU2 group. This model, you can actually write it as on the SU2 group, and you put the Lorentz information in the interaction kernel. This one would be functions on SL2C, on several copies of SL2C. How would you get that? But this is the local Lorentz we are talking about. So the geometry could be as curved as you want in principle in a piecewise flat context. On each simplex, you have Lorentz data. The connection is Lorentz, but then depending how you glue things, as we know from other discrete gravity approaches, you can add. Yes. Yeah, these are pieces of flat Minkowski space. So you take this Lorentzian. Okay. So here, the vertex is what you obtain basically by quantizing a single four-simplex with Lorentz data. And in the kinetic term, you put your prescription for gluing the four simplices together. And for constructing a piecewise. Mm-hmm. Yeah. Well, it gives you local information on the gluing, on the two things. Then check the global information about the simplicial complex. Okay. Okay, what I said, although with a bit more struggle, the relation of the amplitude with simplicial gravity path integrals and spin-found models, depending on the basis of the Hilbert spaces you choose, is valid also here. And the relation again is with the formulation of gravity in the discrete in terms of BF, topological BF in 4D plus constraints. That's how these models are constructed. That is model dependent. Okay, very briefly for the later cosmological application, I will need matter, not only because for any physics you will need matter, but also because the type of observables I'm going to use for extracting an effective cosmological dynamics are relational ones, and I need the matter fields to play the role of clock rods. So very briefly, how do you add matter? Again, longer story short, the model building prescription is the same. Just like you build models in the pure geometry case, guided by the idea that the Feynman amplitude should look like discrete gravity path integrals on a given lattice with group theoretic data. The way you add matter to the models is by doing so in such a way that when you look at the amplitudes, they look like lattice gravity path integrals for gravity coupled to matter, discretized matter. Okay, so you check, ideally, then the situation is always more complicated, but ideally, you take a continuum gravity action for gravity coupled to, I don't know, a scalar field. You discretize it on a lattice, you look at the path integral that you will write with some choice of measure, and then you ask, okay, what is the group field theory that will produce that as a Feynman amplitude? If things were so simple, then you would just write down the action for the group field theory and then take it from there. In practice, you always end up adding data, in this case, real directions, to the domain of the field, which corresponds at the simplicial level of adding data to your simplices. If you have a real scalar field, it's just a real direction. Okay, so the general story, again, just to summarize, you have a class of models that quite generically, you understand as, they produce a sum over simplicial complexes with any topology, weighted by amplitudes, which you can connect with lattice gravity path integrals, and with the appropriate models with spin-found models, which are a covariant way of understanding the dynamics of spin networks. Okay. In fact, this correspondence is historically also one of the main ways in which people got to this type of models. You can start from any spin-found model you like, coming from canonical LQG or categorical constructions of topological field theories. You get to a spin-found model with a choice of amplitudes, each function or representation theoretic data associated to a lattice. If you know them, then you can write down a corresponding group field theory that will produce that amplitude as a Feynman amplitude. Now, in these quantum geometric models, the type of data you add can be motivated also in a different way. You can just look at what sort of states you want to have there. The states have to be the result of quantizing somehow simplicial geometry. In the four-dimensional models I was discussing, when they're based on SU2, you can just take the geometry of a tetrahedron in flat space, in this case in the Minkowski space. You have a set of data which will give you this one possible description, this phase space, and then you have constraints that tell you these are geometric data from which you can reconstruct edge lengths, volume, areas, angles for the tetrahedron. Then you can quantize, you have a Hilbert space for a single tetrahedron, and you realize that the type of data you have are also those of a spin network vertex. You can just have a node and 4 outgoing links for the 4 faces of the tetrahedron labeled by spins. And you have geometric operators for the areas of the triangles, for the volume of the tetrahedron, and so on, that you quantize their geometry, so they become operators acting on the Hilbert space. So there is a quantum geometry story at this simplicial level. Okay, there is equivalent constructions which are more manifestly covariant. And once you have the single body or single particle, if you want, Hilbert space, which is a 3-simplex in 4D, you can write down also a Fock space. And so your states, your generic states, are going to be, collections of such quantum tetrahedra. And what you're doing is to look for, first of all, a second quantized. You can look for a second quantized version of the geometric operators, as you know, by convoluting with your creation annihilation operators that move you around in the Fock space. So create, annihilate quantum tetrahedra. And then you look for a field theory for such quantum many-body system. That's another way in which you can get to the same type of group field theories. When you have 2 different tetrahedra with those data, the gluing of tetrahedra, interestingly, is given by entangling across across the same phase, if you want, or the 2 phases of the tetrahedron. So a generic state is a collection of such tetrahedra, including the glued ones, or equivalently, from a graphical point of view, a collection of spin network vertices, which you can also glue to form closed graphs. And this is where you see that you can also have a direct connection with the kinematical structure of loop quantum gravity, canonical loop quantum gravity, because the states that in loop quantum gravity you associate to a closed graph can be in fact seen as forming a subspace of entangled states in the Fock space, the pre-Fock space, in fact, of this field theory. So somehow what you're doing is writing down a sort of a second quantized reformulation of at least the kinematical structure of loop quantum gravity. Okay, do I have 10 minutes? 5? 7? 7 plus 7? You should not have told me about the plus 7. Okay, the 7. Okay, so let me first wrap up this purely formal part, and then I will briefly go over some, what we do with these models, apart from their construction. Okay, wrapping up, what is the picture, the intuitive picture? You know that we can discretize gravity, we can discretize geometry on lattices. Now, suppose that you start decomposing your lattice into the elementary building blocks. It's a 3-dimensional case. Now the idea is that a lattice is a specific configuration of these building blocks, specific way of gluing. Then you decide to try to write down a quantum field theory of the building blocks. This is what these quantum geometric tensorial field theories are, these group field theories. So it's a quantum field theory of space-time and geometry in the sense that space-time as we know it and geometry as we know it should be reconstructed from particular states in particular regime of this quantum field theory. Although there's field theories defined on some background because you have a group manifold there, that group manifold is not the space-time manifold where we do physics. That space-time manifold has to be reconstructed dynamically. But it treats a quantum spacetime as a sort of a quantum many-body system. So at least at the formal level, many tools become available. And you expect that continuum geometry will have to emerge from some coarse-grained description involving many, if not infinite, such quantum gravity building blocks. It's really like a collective phenomenon. And again, I want to stress, it's all the standard generativistic structures and the dynamics that have to be approximately obtained at some effective level, including flat space. This is not emergent gravity. It's not that we have a theory on flat space and what emerges is just the gravitational interaction or curvature. It's even flat space should be a highly excited collective state. Okay, so this was the story you have seen, and I could have testified that the concrete models end up being involved, technically involved. Yes. Well, as I discussed earlier with Renata, I mean, there are a bunch of parameters of couplings in the fundamental model you start from. If you have at least some clue about the effective geometry, and I will show you, well, I'll try to show you an example of what we do to reconstruct some effective gravitational dynamics, then you can relate those parameters to effective gravitational couplings like G Newton or lambda and so on. At that level, you can maybe try to identify if there is a scale at which this space-time picture emerges. Beforehand, it's not obvious how to have this gravitational interpretation. You can have it, as I said, at the discrete gravity level, because you connect to the gravitational path integral at the discrete, and then you can say, ah, this is G Newton, this is lambda, this is whatever. But whether that remains the interpretation at the effective level or things become messed up, well, that you still have to show. Okay, so given that these models are complicated, you just ask, why bother? And don't believe that we don't ask ourselves that question. It's actually quite frequent. Now, the point is that we know that the summing over lattice geometries and topology is horrible. It's complicated. Now the idea is that, well, we have a generating function for that, and that gives some additional tools. There is some chance, and there are some successes of analytic control over this sum. Moreover, in the more quantum geometry models, you really have quantum field theories. Formally, at least, as I said, there are field theories on a domain with some background metric, although the interpretation is different. And so you have a number of additional tools you can use from quantum field theory. Moreover, I personally at least like this emergent space-time perspective that is embodied and very natural once you pass to this type of formulation. So the key directions, of course, to make sense of these models are, on the one hand, renormalization group analysis. This has to be well-defined field theories. You have to study continuum limits and coarse graining and so on. And then you have to extract effective collective dynamics, possibly interpreted, and you have to check how it matches relativistic gravitational dynamics. Okay, in my 1 minute left, 2 minutes? 2 minutes. No, 2 minutes. So there are two parts that I wanted to discuss: the renormalization group stuff and the effective extraction of effective gravitational physics. I have 2 minutes. So I will just say a sentence about the renormalization stuff, and then I will spend 1.5 minutes on the rest. What I will say is that you have this formulation of lattice gravity path integrals in perturbative expansion. That means that the perturbative expansion has to make sense. for these models, because if it doesn't, well, whatever guideline you had for the construction of the models is not so relevant. So the problem of how exactly you discretize geometry, how you impose conditions of geometricity, the various ambiguities in quantization that you have at the discrete level, they end up being all part of the problem of showing perturbative randomizability of these field theories. So you have a translation of those lattice gravity issues into issues in renormalization, perturbative renormalization of these field theories, of the corresponding field theoretic models. At the non-perturbative level, you want to study the continuum limit. You want to check what are the different phases of these models, and if any of them has to do with gravitational physics, what are the critical points, and so on. Which basically means you want to evaluate all the sums, including the infinitely refined complexes. There's a continuum limit. That translates into the non-perturbative renormalization group flow of these field theories, evaluating the partition function, not just diagram by diagram. So this is the only message. You translate these issues into issues in renormalization, perturbative and non-perturbative of the corresponding quantum geometric field theory model. Okay. And okay, I will tell you about results if you ask, but there are many. It's a lot of people working on that. And we know, for example, that the 3D model I've shown earlier is perturbatively normalizable at all orders. And there are a number of other results. Of course, there's a lot we don't know. And even at the non-perturbative level, there's been both functional randomization group studies of the corresponding models, looking for phase transitions and fixed points, but also analysis at Landau-Ginzburg, because now the mean field is already rich enough and interesting enough, and we know it encodes already the resum dynamics of an infinity of triangulations. Of course, it's a subclass of triangulations, like whenever you write down the classical equations of motion of a field theory, but it's an infinite class. And it's something that if we're trying to do it numerical or analytically at the level of the sum over triangulations, it would be impossible. Anyway, so we have also this type of analysis and results. Now, I use the last minute, unfortunately, I think it's a bit less than 1 minute, to tell you what is the strategy for extracting gravitational dynamics, at least in the simple case of cosmology. Okay, we have to do coarse graining. We have to look at some collective dynamics. That's the spirit. The most coarse-grained dynamics is expected to be indeed the cosmology. From the quantum many-body system point of view, the most coarse-grained dynamics is hydrodynamics. You just look at collective excitations. So we look at this hydrodynamic regime. The hypothesis is sort of, if I want to say it in a fancy way, that the universe is a sort of a quantum gravity fluid of all these atoms, of these building blocks. So we want to extract some effective hydrodynamic equation for a given model of interest. We want to compute relational observables in this regime and then translate the hydrodynamic equations for the collective variables of the fluid into equations for the observables. They have to be then compared with GR. Okay, that's the strategy. And again, we do that. If you were God, you would do it for the full quantum effective action, the full theory. Unfortunately, or fortunately, we are not. And so we look for the simplest approximation, mean field hydrodynamics. Okay. And I said, again, in this quantum geometric model is rich enough to have some content, to have some meaning. In the purely combinatorial models, it would be hopeless to try to see physics at that level. And again, it's an infinity of degrees of freedom already contained here. It's a subset of degrees of freedom. It's a highly non-trivial sector of the theory from the point of view of the discrete structures I started from. Now, there are two general features that are valid for all quantum geometric models. meaning if all models in which you put the discrete geometric data of tetrahedra and simplices and so on properly there. If you've done that, two things are true. The domain of the condensate wave function, the mean field, is in fact isomorphic to the, in fact, diffeomorphic to the space of continuum geometries at a point, spatial geometries at a point. Or in other words, is isomorphic to mini superspace, the space of homogeneous spatial geometries. And if you think about it, it's intuitively clear why it should be the case, because a tetrahedron is basically the blowing up of a single point on a special manifold with this geometry. So you're just looking at the data there, and the condensate density is basically the one particle reduced density. So it has the data of a single tetrahedron that is of a geometry at a point. The other general thing is that when you write down the hydrodynamic equations, which are basically the classical equations of the model you started from, you end up with some nonlinear equation for this wave function, for the mean field. It's hydrodynamic, so it has to be nonlinear. The wave function is defined on mini superspace, so what you end up with is a nonlinear extension of quantum cosmology. And the extension is not added by hand, it's the result of Gauss-graining. So you have quantum cosmology, some linear differential operator on mini superspace acting on your wave function, plus some nonlinear functional of the wave function. Okay, and one could argue, and there's reasons to hope or to believe that this is in fact a more general framework for the cosmological sector of quantum gravity after Gauss-graining. Okay, let me skip. Then you take specific models with scalar fields so that you can use them as clock and rods. You make a number of approximations. You look for condensate states of the simplest type so that you get the Gross-Pitaevsky type equation, so exact condensates. You obtain an hydrodynamic equation, complicated. You can in fact split it if you have clock and rods into a part that does not depend on the rods, homogeneous data, and parts that depend on the rods fields. So it's local information defined relationally. And then you write down, you look at specific subset of observables in the original Fock space. For example, the total volume of your state, meaning you sum the volumes of the tetrahedra in that state. For each, you have a volume operator that you can second quantize. You look for the total volume. When you look at specific subset of condensates, the result is that in expectation value, the volume becomes a function of the values of your clock and rods. This is a relational definition of the volume at the point, where the point is defined by your physical frame. And you can do the same for other observables like the density, energy density of your matter scalar field. But let's just look at the volume. You compute the effective dynamics for such volume. You can do it for the background homogeneous volume, but also for the perturbations. If you just look at the background homogeneous dynamics, so you have a clock that defines your time evolution, and then you have the volume for each value of the clock. And what you find is that at very, very early times, the interactions are subdominant, the interactions, the nonlinear part in the dynamics, and you find a bounce. There is a single turning point for the volume. There is a contracting phase and then an expanding phase with a turning point. And I can tell you under which conditions, but this is quite generic. So there's no Big Bang type singularity, at least looking at the volume. Then the universe keeps expanding. I'm just reading out this behavior from the equations for the observable that I defined to be the volume at a given clock time. And you find the Stardom-Friedman equations in relational clock. Then you can also compute fluctuations of the observables, and they're okay. Then it turns out that when the universe keeps expanding in a bit less generality, but it's still true, at least in a range of models that you can deal with at a more phenomenological level, the universe starts accelerating, where the acceleration is actually directly given by the underlying microscopic interactions between the building blocks, between the quantum tetrahedron. There is a push, and then, at least in a class of models we studied, it looks a bit like a phantom-like dark energy. It goes beyond -1 for the equational state, and then goes back up and approaches a de Sitter phase asymptotically. There's no big rip or similar. Now, again, this is not generic, but it's an example of, and at this level, okay, sorry, just step back, and I've done. At this level, the G Newton is a function of the coupling entering the kinetic part of the model. The interaction coupling instead ends up being related to the asymptotic value of the cosmological constant. Okay, then you can do the same. You can do an analysis of the perturbations as well, but at the moment we only control a bit the dynamics for super horizon perturbations. But we have the tools for extracting an effective quantum gravity modified field theory on a curved cosmological spacetime. Okay, there are a number of lessons that I'm happy to discuss, but I close it here. Before I finally close, let me do my institutional advertising role. Join the International Society for Quantum Gravity if you're interested in quantum gravity. Don't care what approach you work on, or if you're more mathematical inclined, physical inclined, phenomenology inclined. If you're an experimentalist, but that doesn't apply here, but you're interested in quantum gravity phenomenology, join and help. It's for free. And so I'm not asking money now. Thank you.
Thank you, Daniele. So in the end, you took 60 minutes. But if there is any urgent short question, please, Neil.
Oh. I can show you why the eye has to be there in one model. Already in the 3D. Sorry? Yes. I'm going for the Riemannian one, otherwise you would be less interested in the appearance of the eye in the Lorentzian case. Yes, Bulatov. This one. I here. So this is the result of computing the amplitude. It's not the interpretation of the amplitude. So it appears with an I in front of this action. It mathematically comes from the fact that this term here is basically a bunch of plane waves. Plane waves on the phase space, which is the cotangent bundle of the group, the SU2 group that I started from. So mathematically it comes from there, the I. Why should be physically there? Because 3D gravity has to impose flatness everywhere. And this flatness imposition that you see in this representation is the result of integrating the triad. If you were integrating the triad without the I, you would not get the delta for each edge. This is a theory of quantum Riemannian geometries. 3 geometries, of course. For the BF model, for example, where it's just a topological theory, is exactly the same. It's literally the same, with the curvature now associated to triangles rather than edges. But exactly the same theory. Sorry? The I is still there because the non-topological nature comes into a complicated measure in front, imposing geometricity constraints. But this story with plane waves and so on will be exactly the same. You will still get the I.
Okay, very good. So let's thank Daniel again.
Yeah. Thank you.